All right, everybody. This is 1 o'clock here in Denmark. So thank you for being here, all of you, and welcome to the webinar where we are launching FarmConners Wind Farm Control benchmark. So these are some recommended practices to follow during this webinar. So please remember to mute your microphone and turn off your camera if you have not done already. And feel free to type your questions in the chat section below, which we will go through in the Q&A session. And note that the webinar is recorded for further dissemination, and it will be put up to the Wind Farm Control YouTube channel. And the slides will also be shared along with the webinar video recordings in the proper dissemination channels. So here is the agenda for the webinar. For the first 30-35 minutes, we will give you an overview of the benchmark. And then following 10 minutes, we will do a short demonstration of the benchmark documentation. We will show you how to participate. We will briefly mention how to access the data and point to some examples of the data extraction. And then the session will end with a Q&A. So having this extensive benchmark wouldn't really work without having a lot of clever people on board. So I would like to thank to the benchmark organizers. And then I am Tuğfe Göçmen. I will be your host, main host for today. And then during the presentation, you will also hear from my colleagues under FarmConners, who are Ishan, Irene, Lipo, and Toma. So let's start with a brief description of the project. What is it, and who actually are involved in FarmConners? So FarmConners is an EU project, Horizon 2020, is a coordination action on wind farm control. And wind farm flow control technology is bringing a collaborative approach to wind power plant design and operation. It promises to mitigate the losses due to turbine-turbine interaction within a wind farm. The concept actually has been around for more than 2 decades. Within FarmConners, we are planning to pave the way for industrialization, further industrialization of wind farm control technology. And we have several research institutes, industry, and certification agencies on board. You can see our list of partners here. DTU is the coordinator of the project. Then we have TU Munich, KU Leuven, SINTEF, SENAR, TU Delft, Forwind, and Vestas as our research partners. And then from the industry and the certification agencies, we have Vestas, the NVGL, NG Green, Inoji, and Ore Catapult. So why launch a benchmark on wind farm control? As I said earlier, wind farm control has been around for 2 decades and is currently under development at a number of research institutes, industry, and certification agencies globally. However, the uncertainty remains high, and in FarmConners, we aim to remove the barriers for commercial implementation of wind farm control. And it's only possible by coordinating a reliable assessment of the state-of-the-art in this technology. In order to truly assess the performance of wind farm controllers, the efficiency of the wind farm control models themselves should be evaluated. Because if you would like to increase confidence in the technology, you would like to increase the confidence in the wind farm control models that are feeding to this technology. Therefore, there is a need for common test cases to demonstrate the potential benefits of wind farm control, such as increased power production and mitigation of loads. Accordingly, in FarmConners, we are planning to evaluate the performance of wind farm control-oriented models under controlled operation. On that extent, FarmConners benchmark is actually an extension of the international validation and verification framework, the efforts related to VNV on wind farm control models, such as wake bench, to include wind farm control operation in the wake research. In terms of the infrastructure of the benchmark, we have 3 main platforms, you can say. The first one being the public Git repository that includes some example cases, which I will point to at the later stage in this presentation. Then we have a version track documentation that is directly linked to the Git itself. Over there, you can find detailed information about the benchmark, such as the test cases, provided datasets, quantities of interest, expected results from your side, and the deadlines we expect you to follow. And also, the registration should be done filling a form on how to participate in this documentation, which I will also demonstrate at the end of the webinar. After you register, you will get a link to a personal cloud folder, and only you will have the right access to it, and the read access will be shared between you and the benchmark organizers themselves, meaning that the participants won't be able to see each other's folders and results. I would like to present you the test cases we have come up with in order to fully assess the performance of the wind farm control-oriented models. The first one being the single full wake under wind farm control. So we are looking at a two-turbine configuration where the first turbine is being controlled. And the control settings on the first turbine is different per dataset, but it includes axial induction and wake steering. Also, the spacing between those two turbines can be different per dataset. And it's important to note that for some of the dataset, this two-turbine configuration is actually a subset of the wind farm layout itself. So there should be expected some additional blockage effects. For all the test cases that I will present right now, there will be two types of folders, two types of structures. The first one being the calibration, where you will get both the input and the output features for your model, meaning information from both of the turbines in this case. And then in the blind folder, you will get only the input features, for this case at the downstream turbine. And you are expected to upload your results for the output features that is coming out of your wind farm control-oriented models. The second test case I would like to present is the single partial wake under wind farm control. Very similar to the single full wake case, but this time, as you can see, there is a lateral spacing between the two turbines. Still, the control settings are applied to the first turbine, and they can be different per dataset, still includes axial induction and wake steering. The spacing between the turbines, both axially and laterally, can be different per dataset. The third case I would like to mention is the multiple wake under wind farm control. And over there, we are investigating a row of turbines. So this time, control settings are not necessarily limited to the first turbine, but it can go up to several turbines. The control settings themselves will be again varying per dataset, still includes axial induction and wake steering, and the spacing in between the turbines are not necessarily uniform within the dataset itself, and they are different in between the datasets. Also, the number of turbines that are including in particular dataset are different from each other. So what are those datasets? So far, we have an extensive LES large eddy simulation database that are fed from two big EU projects, Total Control and CL-Windcon. And then we also have the wind tunnel experiments that are conducted under the CL-Windcon projects in Politecnico di Milano Wind Tunnel. And then we have SMV wind farm field data from ANG Green, which is an onshore site located in France. With this, I would like to leave the floor to my colleague Ishan to describe Total Control LES dataset.
Thank you, Tufik, for that introduction. Hi everyone. I am Ishan Sood from KU Leuven, Belgium, a PhD student working on the Total Control Horizon 2020 research project. Tufik, could you please go to the next slide? Okay, so one of the main goals in the Total Control research project is the development of a virtual wind farm environment for the testing of wind farm control strategies. To this end, at KU Leuven, we have developed a SP-Wind, a pseudo-spectral aeroelastic large eddy simulation code. Using SP-Wind, we have developed 5 different precursor inflow fields to cover different atmospheric boundary conditions for wind farm operation. These inflow fields comprise of two pressure-driven boundary-like cases comprising of different reference lengths, as can be seen on the figure on the right. And also we have 3 different conventionally neutral boundary-like cases categorized by a capping inversion on top of a turbulent boundary layer. The wind farms used for our wind farm simulations is a Total Control reference wind power plant comprising of 32 DTU 10 megawatt turbines, as can be seen in the first figure on the right, staggered in vertically and horizontally by 5D spacing between the turbines. Using our 5 inflow conditions and the reference wind power plant, we have comprised of 10 wind farm simulations, in which staggered over 4 different wind inflow directions, which is achieved by rotating the wind farm to simulate different directions of the wind. All the data regarding the precursor inflow fields, as well as the wind farm simulations, is publicly available on Zenodo. It must be noted that so far, these wind farm simulations are using a normal operation, such that the turbine are currently operating on grading approach to provide a benchmark for comparison for normal operation. And during the course of the Total Control project, we'll also be running some controlled operations in our wind farms. And to all the participants who are interested in total control data set, you will be notified personally when the total controlled data sets have been published online. So the data sets that have been selected as part of the FarmConners Wind Farm Control benchmark are a subset of the data sets that I've already mentioned. In particular, we have chosen the pressure-driven boundary layer cases to simulate the single full wake, the multiple full wake, and the single partial wake. In each of these cases, the wind farm has been rotated by a particular angle to simulate the inflow. For example, in the PDK 90 case, the wind farm has been rotated by 90 degrees to have aligned arrangement of all our turbines. In the single full wake data set, we have the first two turbines in which the first turbine has a free flow coming inside and the second turbine is fully waked. Similarly, in the multiple full wake case, we have information about 8 turbines, which have been represented by the box in the PDK 90 case. In the single partial wake case, we have the 2 turbines in the shown in the box in the PDK 0 case, where we have the second turbine partially waked by the upstream turbine. The outputs present in all of these data in database comprises of a flow size in the x-axis direction, which has a velocity time series of all the velocity components at 10-second intervals. We also have for the turbine performance data for the highlighted turbines, which comprises of the power, thrust, pitch, rotation speed at a much faster 1-second interval. Loading information for the turbines is also available, such as the root flap-wise moment and the edge-wise moments at an even faster 100 Hz resolution. It must be noted that additional data is also available at faster including of the whole velocity field on KU Leuven internal archives, and this data would be available upon request.
Thank you so much, Ishan. Yeah. We can now continue with CL-Windcon LES data with Irene.
Okay, hello everyone. I'm gonna tell about the high fidelity simulations in SOWFA that were provided by the project CL-Windcon. So please, yeah. So maybe you know already CL-Windcon was a Horizon 2020 project that ended up last year that was entirely devoted to wind farm flow control, and in which we were using 3 pillars for model validation and control verification, and also for control-oriented model calibration, which is the subject here. And regarding the high-fidelity simulations that were performed in SOWFA, and we are describing here, this was a work performed by a team led by my colleague Sugoi Gomez-Iradi in CNR, in collaboration with Politecnico di Milano, and also under an award of Supercomputing Awards of the PRAISE program. So as you probably know, SOWFA is an LES open source software and framework, which is built on top of CFD OpenFOAM toolkit, and also the well-known NREL's servoelastic wind turbine simulation tool, OpenFast. So for the whole dataset, we have an extensive amount of data, which is published in Zenodo, and also available at CNR's FPT under request. And there we can find different scenarios that were simulated. First, a single wind turbine, and then 3 wind turbine and 9 wind turbine, which are shown, the layouts are shown on the right for the 3 and 9 turbine cases, all using 10 megawatts reference wind turbine, as in the case of total control. So the whole dataset is a combination of different ambient conditions, wind speeds, turbulence intensity, roughness lengths, and also different control actuations that could be expected in wind farm control, like yaw misalignment and some values of derating. The outputs are both the turbine response, the whole turbine response is taken from OpenFast, and also the flow slices of the different wind conditions along different wind turbine wakes, and maybe we have some time afterwards to see. So from this big, extensive data set, we took a subset, as Tufe was commenting before, to perform a FarmConners benchmark. And in this case, we are focusing on FarmConners single full wake and multiple wake cases by making use of the 3 turbine and the 9 turbine layouts. The ambient conditions that have been selected as relevant cases for the intended benchmark are the mean speed 7.7 meters per second, a turbulence intensity of 5.39%, and shear height of 1 millimeter. Here, the actuation is based on yaw misalignment, so with different yaw angles, and a part of the actuation is used for calibration, and another part for the blind exercise. So in terms of the flow, as I was commenting before, we have the final step, the volumetric solution in order to restart or to analyze the entire domain, and also the flow slices that I was commenting before that are taken each 10 seconds. And for the turbine response, we have each 30 milliseconds, both the turbine properties and also the detailed analysis of conditions of the turbine and also loads, which are kind of interest. But for the benchmark, we are making a selection, and this is in the documentation, of 3 types of loads of main interest for the exercise. Thank you.
Thank you so much, Irene. So we are staying within CL-Windcon and going for the wind tunnel experiments with Filippo.
Okay, good afternoon, everyone. I'm Filippo Campagnolo, and working for the Technical University of Munich. And I will provide an explanation of a view of which kind of tests have been conducted within CL-Windcon and are provided for this benchmark. So thank you, Tufe. So the tests have been conducted in the wind tunnel of the Politecnico di Milano, and specifically in the civil boundary layer, in the civil test section. It is quite large, as a section has the width of 40 meters and the height is almost 4 meters. And next, please. And also the test section is equipped, in the test section it's possible to reproduce a boundary layer by placing spires at the inlet or roughness element on the ground, and is also equipped with a turntable where the models have been fixed to, so that to simulate different wind direction. Thank you. Next. Just a brief overview, just to clarify that the models were all identical. G1's model, that's name we were given to the scale models that has diameter of 1.1 meter. And what is important is that they are fully actuated, so with torque control, individual pitch control, yaw control, as well as quite well sensorized. So there are loads sensor on the shaft and at the tower base. So fully automated, fully controlled like a real wind turbine. So please next. Concerning the first test case, single full wake, the experimental setup, we were being using up to 2 G1 scale models, longitudinally spaced by diameters, and we were simulating 2 boundary layers, one typical of offshore with a turbulence intensity of 6%, and one typical of onshore with a turbulence intensity of 30%. Then which kind of operating conditions are available for the model calibration? In this case, basically we will provide you data that were obtained by testing a single G1 operated at 3 yaw misalignment, so like -20 + 20, 0, and 2 power set points. And also we will provide you data that were obtained by testing 2 aligned G1s operated at null yaw misalignment angles. For both, clearly all these for both inflows. The data set, so which kind of data are available for the model calibration. For the single G1s, you have measurements of the wake shed by single G1 and measured at 3 different positions downstream, and also all available signals that were measured on both the G1s, so controlled inputs, loads, everything. For the 2 aligned G1 cases, just the signals of the G1s. For the blind testing case, we have more operating conditions, so that were obtained by testing a single G1 for 7 yaw misalignment angle and 1 power set points, and also 2 G1s aligned However, they were misaligned both the upstream and downstream with 50 combinations of yaw misalignment. Then the data set that is available for the blind test is just the experimental setup, so where the turbines were located. We were measuring the speed in front of the cluster, so you will know exactly where the speed was measured, and we will provide you the speed measured by the pitot tube, the mass of our scaled cluster, and also all the G1's control inputs, means like orientation on nacelle, blade speed, and rotor speed. For the partial wake case, the experimental setup is quite similar. So 2 G1s, however, they were laterally spaced half diameter or 0.6 diameter. Again, two inflow conditions. And next, please. And again, operating condition for the model calibration, 2 G1s, laterally spaced 0.5D. The upstream one operated at 2 yaw misalignment, the downstream one instead at null yaw misalignment, and you have all the G1 signals. While for the blind test, we have 2 G1s, laterally spaced 0.6 diameter, and this was achieved by rotating the turntable approximately 7 degrees. And we were testing 25 combinations of the yaw misalignment for both turbines. And again, you have similar for the blind test, you have similar kind of data that are provided. So where the turbines were located, speed measured by the pitot tube, and all G1's control inputs. Finally, for the multiple wake case, it's quite interesting. Again, the setup here, we were using up to 3 G1s, longitudinally spaced 5D and laterally spaced aligned, and also laterally spaced 0.5 and 0.6D. Again, 2 inflows as before. And for the model's calibration, quite some operating conditions are available. So we have operating condition where we had just 2 aligned G1s operating at 2 different sets of yaw misalignment or 2 different sets of power set points. And also we had 2 G1s laterally spaced half diameter and operated again at 2 sets of yaw misalignment. And also we had 3 aligned and 0.6 diameter laterally spaced G1s operated at null yaw misalignment. And so for the calibration, similar for the 2 G1 cases, you have measurement of the wake after the downstream G1 along horizontal lines and the 2 different downstream positions and all G1 signals. And for the 3 G1 cases, instead, you adjust all G1 signals. And similarly for the blind test, we have a lot of operating conditions. So 2 aligned G1s operating again at 2 sets of yaw misalignment, clearly different than before, different than these sets of yaw misalignment used for the calibration, and 3 sets of power set points. Again, also for the 2 G1s laterally spaced half diameter, we have again 2 sets of yaw misalignment. And also for the 3 G1s, for 3 aligned G1s, we have 50 combinations of upstream and downstream G1s yaw misalignment, while the third one was kept aligned with the flow. And for the 3 G1s laterally spaced 0.6D, we have 25 combinations of upstream, downstream G1s yaw misalignment, and the third instead was operating in null yaw misalignment. Okay, so this is an overview, and again, the data set is similar as before, so inflow data measured by the pitot stream and all G1's control inputs. So which kind of data are also provided? We provide measurement of the inflow that was recorded measuring the wind tunnel with hot wire probes, 4 diameter upstream of the first G1s, and we will provide like a map of the flow of the mean longitudinal wind speed and the turbulence intensity at 880 points, 4 diameter upstream. Also, we provide the G1 fast model, and the polars were tuned with experimental data. However, we don't provide the control algorithm that was controlling the turbine. And we also provide MATLAB scripts for the post-processing. Say how to use the data. So basically, we have an Excel file that is called test metrics that lists all the available data for every test cases and both calibration and blind test. And basically, please next, Tufe. This Excel file contains 2 Excel sheets. The first one that calls test metric that lists for all cases the where the wind turbines data have been saved in, where the wakes data have been saved in, the inflow average speed, turbulence intensity, the operating conditions of the G1s, the layout, so lateral spacing between the turbines or the turntable rotation, which kind of measurements, wake measurements were performed, and also other info. And please next, we have a second Excel sheet that is data description that reports where the turbine were placed in the wind tunnel and where the wind tunnel MapMast AP2 was located, the adapted reference frame for the wind turbines and wake data. And please next, and the data organized in MATLAB structures for both the wind turbine and the flow data. And as you can see, we have MATLAB structure where basically we have the data for all the turbines that, for example, are organized very clearly and also is reported, which is the unit of measurement and the sampling frequency. Okay.
Thank you so much, Filippo. Now we are going to the wind farm field data. Thomas will be presenting that.
Hello everyone, my name is Thomas Duc and I work for Engine, which is a French company that develops, builds and operates wind farm. And today I'm going to talk about you SMV wind farm, which is the wind farm on which we run some wind farm control cases a few years ago. So here is an overview of the wind farm. So it consists of 7 wind turbines, MM82 Senvion, 2 megawatts and 80-meter hub height in an onshore terrain in the north of France. So you see the map here. The terrain is not complex. It's mainly fields and crops for very open and flat terrain. We just have to mention a small forest, which is located southern of the farm that might add a bit of turbulence. And in this wind farm field data, you will be able to test the scenarios of single and multiple wake case. And I have to mention that the wind farm control tests were realized in the scope of a French national project called SmartEol. And basically it was realized on the SMV6 turbine and we were mostly looking at the effects on the SMV5 downstream turbine, and we tested both wake steering and axial induction control. So about the available data which is made for this benchmark exercise, so we will be providing the SCADA data of all the 7 wind turbines in the farm as a form of 10-minute statistics that comprise both mean, standard deviation, minimum and maximum value for the most important channels of the turbines which are listed in the table above. And the duration of this sharing will be almost 2.5 years, which includes the field test number 2 that we realized in the scope of the SmartEol project. And this total data set will be split in 3 periods. So 12 months will be used for the calibration, 12 months will be used for a blind test under normal operation, and then the 5 remaining months will be used for the wind farm control cases that we run during the SmartEol field test number 2. And along with this SCADA data, there will also be some static information. So basically the coordinates of the wind turbines in the farm, and also the guaranteed power curves and the thrust curves of the wind turbines. And during the field test number 2, we also had a WindCube V2 LiDAR that was measuring the incoming inflow close to SMV6 wind turbine. So we will be also sharing this data set for the benchmark exercise. Some comments about the data pre-processing. So I did work to clean and pre-process the SCADA data so that it can be really easily and quickly be used in the FarmConners benchmark exercise, meaning that there are lots of pre-processing to remove inconsistencies or curtailments or correcting biases in the data. And now the available data for the benchmark, I think, can be used pretty straightforward in the exercises. And with the data, you will receive also a kind of README document which explains quickly all these pre-processing treatments that have been done and how you need to use this data for the different exercises. One big remark is that contrary to the other data sets for the benchmark, we cannot make this data publicly available. So you will have to sign an NDA just to get access to the data. And this will be presented later on by. And just a quick glimpse at the first the wind farm control field test we did on the scope of SmartL. So on the rake steering test, we applied a constant misalignment on turbine SMV6. And based on the field data, we were able to observe a very clear wake deflection looking at SMV5 data. So the exercise will be focusing in the sector of the full wake where we see the high deflection of the wake, so between 200 and 215 degrees. On the other hand, for the axial induction control, we applied some curtailment on SMV6 turbine. However, for this field test, we had very few data points available, so it might be more difficult to analyze the output of the wind farm control for the axial induction control. So I'm done with the presentation of the wind farm control benchmark for field data, and I'm giving back the presentation to Tufik.
Thank you so much, Thomas. So given all these very interesting data sets and the test cases, the rest of the webinar is going to be more about you and what we expect from your side, and also getting the results from your side on which quantities we would like to evaluate their performances on. So first, let's start with the quantities of interest. So the first output feature we will be looking at will be the power gain under wind farm controlled operations at the wind farm scale. So we will have the power produced by each and every turbine under wind farm control operation, normalized by the normal operation conditions. We have also introduced wake loss reduction as an attempt to avoid potential errors originating from conversion of wind speed to power. Over here, U indicated can be either the hub height or the rotor effective wind speed, which is the spatial average wind speed over the rotor, depending on the model capability that you're using. Another quantity of interest we would like to look at is the reduction in wake-headed turbulence intensity, which can be correlated, which can give us an indication of potential reduction in the loads further downstream. If the model is capable, we have also defined a load alleviation as the quantity of interest, which will be based on damage equivalent loads for both flapwise, shaft, and tower bottom bending moments. So what to upload from your side? One thing to note is that the deadline to upload your results is the end of this year, and you will be getting the dataset as soon as you register, which is open starting today. So what to upload at minimum is a brief description of the model that you have used, including relevant references attached to that description. And then we would like to have the power produced by the turbines, given the test case, given the data set based on the layout. We would also like to get the hub height and or rotor effective wind speed at the turbines or at the measurement locations. For example, for the wind tunnel, there were wake measurement locations behind the turbines. Wherever applicable, depending on the fidelity of your model, we also expect you to upload flapwise root bending moment at the turbines, vectoral sum of the shaft bending moment at the turbines, and vectoral sum of the tower bottom bending moment at the turbines. There are very clear instructions that is listed in the documentation, so please follow those instructions before you upload your results. Speaking of the documentations, here we can have a little demonstration of what those two platforms look like for the FarmConners benchmark. So for our Git, which is a public Git, you can see there are two folders. One is feeding the information to the documentation itself, and one is describing the example cases. And if you click on the example cases, you can see two selected here. One from the wind farm field data Thomas mentioned, and you can see how to read basic information about how to read the data set in data frames and how to have the basic plotting to see either within the wind farm itself or in between the turbine features. And then the second example is looking at a little piece, a little pickle file that is under the CL-Windcon LES very extensive database. So you can always refer back to them if you need any help in seeing some of the data sets, if you need an example to read some of the data set. And then within the Git, there is also a direct link to our documentation, which will be the key document that is also regularly updated. And you are very much encouraged to check it also regularly to see the updates. Over here, you can see the whole navigation pane, pretty much everything we talked about today. It starts with provided datasets, so extensive information, and also relevant figures and references to all the cases that is mentioned today. We also have the test cases listed in the navigation pane, all the 3 listed here. And if you actually click on one of the cases, for example, the single wake, you can see what the available datasets are for that particular benchmark. And you can also see the expected model results with their naming conventions. So how to upload them or which parameters to upload. You can also see the quantities of interest, which I briefly mentioned over here. You can read a lot more details about them and also the motivations why we think they are a quantity of interest. If you are in doubt in any of the abbreviation or the symbol, you're encouraged to check this general taxonomy and nomenclature page, which can give you an overview of certain abbreviation or symbols we have used overall in the benchmark. And possibly the most important part in this documentation, at least for today, in the beginning of the benchmark, is how to participate section. And over there, there is already an online form that you are expected to fill. So within this online form, the first part is all about your personal information, your name and your email, which will be used for the communication back and forth. So you will get, for example, the personal link to your cloud folder to upload the results. And you will also get, for example, server accesses and direct links for other datasets personally through your email. So which datasets that you are choosing under the test cases over there is listed in the second part of this registration form. So I strongly encourage you to go and maybe have a second read on each individual test cases, pick up the dataset that is the most interesting to you, and start clicking on them. You are not limited to click only one of them. You can choose all of them, which will be really good for our side. So if you are to choose wind farm field data, just like Thomas mentioned, this is actually protected under an NDA. So this NDA, the template for this, can be found in the link here, and you are advised to follow the instructions given on the first page. After you filled in your information and chose all the dataset that you are interested in under the test cases, submit the form, and we as the benchmark organizers will get a notification of which dataset you would like to participate in and send you those datasets, access link to those datasets, as well as the personal cloud folder link. This brings me to the end of the demonstration, which means end of the presentation part as well. So we will be very happy to take some questions if they were coming up in the chat place.
So far, we didn't get any questions in the chat, but of course, you can still just write them there or even raise your hand and you will get the word. But maybe, Tuve, while we are waiting for questions, maybe you could tell us again why people should participate in this benchmark.
Yes, of course. So the following steps for the benchmark, for example, will be to see your model in comparison with all the other models or a number of other models that are available within literature or that are in use in a couple of researchers, and see how your model performs against them, and see how overall trends in the wind farm control, in terms of wind farm control models, look like. All these results, your uploaded results, are also going to be compiled under these quantities of interest that I just defined. And then they will be compiled into a presentation for the Wind Energy Science Conference next year, which is at the end of May next year, 2021. And then following the conference, we will also be publishing a paper describing the results under for each test case per data set, given the quantities of interest. So by participating in this benchmark, you're also taking a co-authorship seat in that paper coming up, as well as the co-authorship seat in the presentation that is going to be in the Energy Science Conference.
Okay, sorry, thanks Tuve, I just started talking. I'm Constanze Körle from SINTEF. So we still didn't get any question, but you said that people would be able to join in the publication. What if I would like to keep my results anonymous, so that I would like to compare my results to other models that are out there, but still I want to keep it anonymous? Is that possible?
Yes, of course, and that's a very good question, actually. It might be the case for several people that they would like to keep it. So the approach to have that actually is just giving the participation ID and a brief description, maybe just a mention of the model if it's already used, or a brief description of the model that has been presented in this comparative analysis at the end of the benchmark. So all the results, let's say, will be anonymous. So you will have a participant ID, participant 1, 2, 3, 4, 5, and then they will be compared up against each other, given the test case and the data set.
Okay. Thanks. And now we actually got a question. So, Paul, you can ask it actually if you want to.
Okay. Hi, this is Paul Thomassen from Simis in Norway. So we're working with aeroelastic software. So I'm trying to understand how we might or might not fit into the benchmarking. So I saw that OpenFast is used already. That was my understanding, that OpenFast is used already. So I was wondering if people are planning to use other aeroelastic software than OpenFast.
Maybe they will be within this benchmark, but I'm not sure. For example, Irene, do you know if there's anyone else used any other aeroelastic tool other than OpenFast for CL-Windcon LES data?
From CL-Windcon and in the dataset that we already have, it's based on OpenFast. But I think that in terms of being used for the benchmark, I guess any of the other models can be used, and that will be interesting as well to see the effects and how they are taken into account.
Definitely, because except of the wind farm field dataset from SME Wind Farm, all the other datasets have the turbine models in and a very detailed inflow. So you're more than welcome to set up the aeroelastic simulation based on that.
How about DTU? Is DTU planning to use Hawk2 or some of your software? Well, I guess the Hawk2 is the aeroelastic software used.
Yes.
DTU.
Yes, so we are currently working sort of the mid-fidelity tools that are bringing dynamic wake meandering concept together with Hawk2 and having a little bit more numerical efficiency, and that will be a part of the benchmark, for example. I mean, we will participate in the benchmark with that code, I should say. I expect several more colleagues from DTU. They have already showed interest in participating with even lower cost tools. And we will see how many we will be in the end.
Yeah, I guess I get one more question also. Yeah, as you understand, I'm not too familiar with the project. So will people be writing their control systems or rewriting their control systems like on a that will run in aeroelastic codes, or is that not a part of? Is that probably not a part of this benchmark?
As far as I know, we're not sharing the controllers. Correct me if I'm wrong, Filippo, but that was a discussion we had last time, isn't it?
Yes, I mean, at least I'm speaking for wind tunnel, so we are not sharing the controller, so we are just sharing the controller inputs. And so with controller inputs, for example, it could be possible to take the control inputs as uses in a simulation or elastic simulation and gets as output the loads. Otherwise, of course, for example, for the wind tunnel, we'll provide a fast model, so someone could build the controller because all the information are available. Or if they're really interested, the controller could be shared, but it should be something that should be discussed or could be shared at the individual basis. So it's something that should be discussed.
And I can say that it is the same for the 10 megawatt cases, which was used in the total control LES. So there's an open source controller for that also, which can be shared upon request.
Okay, and then we got a second question from Fred. Do you have the words if you want?
Yeah, can you hear me?
Yes,
Yes, Fred.
perfect.
Okay, cool. Hi, Tufa. As far as I understood, you plan to focus mainly on integral quantities for the comparison, like wind turbine powers and mean velocities. I'm just wondering if it could be interesting to have some comparison of some velocity profiles, typically for the yacht case. Just because sometimes, you know, when you work with some integrated quantities, you may have some error compensations. And I think like just that, yeah, having some comparisons of the velocity profiles or turbulence intensity profiles may also be interesting.
That is a very good point. I definitely agree to that. It will, of course, depend on the fidelity or the capability of the model the participants plan to use. But if we get enough or higher end of the fidelity that is coming from people that we can have a meaningful comparison of the profiles, that would definitely be interesting to look at. But back to your point about the integrated quantities, they are, let's say, mainly integrated in space. So our plan is to get the timestamped time series from all these expected uploaded parameters, expected parameters from your side, so that we can actually have not the mean comparison or the median comparison, but we can have a look at how the results spread for a given downstream distance, for example, and per case and per quantity of interest. So we would like to look at those statistical properties as well: median, standard deviation, min, and max if possible.
Oh, okay, understood. Thank you.
Maybe one more thing I should mention is that after you submit your results, we will, in the same Git I just showed in this link over here, we will also be sharing the notebooks that we do the post-processing of your results and how we obtain the plots that we have obtained. That will also be open source, and you can come and comment on it. We will be in communication throughout the benchmark as well on that regard.
Okay. There are no further questions from the audience right now.
Okay. Just feel free to write to us. Now there are a lot of contact us buttons that is listed under the documentation, so you can use that. You can also use the emails, and you can look up for us. You can also write on LinkedIn, and then we can take it further if you like. So this webinar, this recording is also going to the YouTube. I will share the link on LinkedIn as well, together with the slides. So if you come up with a question further down the road, feel free to write to us. And please register. And we are so excited to see a meaningful number of participants so that we can get the full benefit of this benchmark that, you know, took us quite some time to bring together.
I suggest we give applause to Tufa and the team.
Thank you, everybody.
Thank you.